All right. Greetings, YouTube. Beautiful Mind here. Welcome. Congratulations on surviving 2021. Be aware that you have survived 100% of all your obstacles of the past, all right? You have made it this far. Also, be aware that we didn't come this far to just come this far, right? So I encourage you to do your best. I'm Professor Pfeiffer, aka Beautiful Mind, and this is going to serve as the initial lecture for College Algebra 2 for spring of 2022, okay? So we're going to open up this semester. We're going to start off by starting with a section in Chapter 1 around graphs and functions, namely Section 1.7, inverse functions. Some objectives that we like to take a look at. We like to define an inverse function, find the inverse function, use inverse functions to find the rate of a function, and apply inverse functions in the real world. Okay. So first we have the definition of a one-to-one function. A function is called a one-to-one function if each y value in the range corresponds to only one x value in the domain. So in other words, every y corresponds to exactly one x. You don't have one y corresponding to two different x's. Namely, an example of something where one y corresponds to two different x's would be like a U-shaped graph or the parabola. If you think about a parabola, like let me just do a quick sketch, right? We have our xy plane, and say we consider a parabola, right? A U-shaped curve. Notice that we have several examples where one y corresponds to two different x's, right? So this is an example of something that's not one-to-one because we have a y value that has two different x values, right? So one-to-one means that every y corresponds to exactly one x, okay? Okay. So then, we're gonna, another way to look at this notion of every y correspond to exactly one x, we can use, this is something that's called a correspondence diagram. So again, for a one-to-one function, every y value in the range corresponds to only one x value in the domain. The range are the set of outputs of a function, the domain are the set of inputs of a function, right? So notice that every y corresponds to exactly one x, one x, so on and so on, right? Every y corresponds to exactly one x. So this is an example of a function that is one-to-one. Here's an example of a function that's not to one-to-one. We have one y value that corresponds to two different x values, right? So in a correspondence diagram, I call that like a merge. You have two different x's going to the same y. I call that a merge. A merge is an example of something that's not one-to-one. You have one y value corresponding to two different x values, okay? So even though this function is one-to-one, where every y corresponds to exactly one x, you don't have one y corresponding to two different x's. This is an example of something that's not a function, right? Even though it's one-to-one, this is not a function, right? In the sense that we have repeating x's, we have one x going to two different y's. So this is an example of something that's not a function. Okay. Okay. Hopefully that's okay. So we have a test to determine whether a function is one-to-one. A function is one-to-one if no horizontal line intersects the graph of f in more than one point. So when we're looking at the graph of the function, if we can, as long as we can draw a horizontal line and it does not touch the graph at more than one spot, then we say that the graph is one-to-one. In other words, every y corresponds to exactly one x. Okay, so we're actually use the horizontal line test to determine which of the following functions are one-to-one. Now, at this point, we should be comfortable with graphing these. Since this is a remote asynchronous class, obviously you can use like graphing utilities like either a graphing calculator. I know a lot of students like to use this thing. There are a couple of free graphing tools. One of them is Algebra.com, and I'll just kind of write it G as best I can, Algebra.com. And I know students also like to use things, I think something called Desmos.com. I think that's how the second one is called. But basically what these are free online graphing tools. So you can like type in these formulas and look at the graph quickly and easily. It is encouraged or recommended that you have a graphing utility, like a graphing calculator. But again, this is a remote asynchronous course. So you can use these websites and it'll kind of get the job done. All right. But if we were to look at these graphs, we're just asked to look at the graph and then see if it passes or fails the horizontal line test, right? So I'm just going to use my computer generated graphs that I have already done. So for the first one, we have y equals mx plus b. So the b is 5, our y-intercept is 5, the slope is 2, right? You see the y-intercept of 5, you go up 2 and over 1, you see the slope of 2, right? So here's the graph of part A. So notice it's just a straight diagonal line. So no matter where we put a horizontal line, like I'm just gonna kind of put one in there. And let's go like style. Let's thicken that up and let's go like this. Okay. So no matter where we put this horizontal line, it touches the graph only once, right? We can try several different places. No matter where we put the horizontal line, it only touches the graph once. So this is an example of something that passes the horizontal line test. So because no horizontal line intersects the graph of f in more than one point, then we say that this function is one-to-one, right? Before we look at the graph of the second one, let's try to do a quick review, right? What's the parent function here? What's the main function? The parent function here is a parabola, is x squared. It's a U-shaped curve. So if we think about transformations, we take a U-shaped curve and this says to move it down by 1 unit. So all this is a U-shaped curve that we move down by 1. So we have that here, right? So if I think we mentioned earlier, as we use the parabola as an example of something that fails the horizontal line test, right? So notice we can draw a horizontal line and it crosses the graph. It touches the graph more than once. So this is an example of something that fails the horizontal line test. So we say this is not one-to-one. Even though this is a function, it's not one-to-one. And we're gonna extend this notion of a function being one-to-one. We're going to send it a little bit further. But for right now, this is an example of something that fails the horizontal line test, i.e., this is not one-to-one, i.e., every y does not correspond to exactly one x. We have several examples of one y that corresponds to two different x's. Okay, right? So whenever we say one-to-one, that's the exact same as saying it passes the horizontal line test, which is the exact same as saying every y corresponds to exactly one x, right? So we're saying the same thing 3 different ways. Let's keep it going. Okay, it's okay. I meant to look at this in advance, but so here we have 2 times the square root of x, right? Square root of x from college algebra 1. The parent function is root x. So that graph, all that is the top half of a sideways parabola. So then if we think of transformations, we multiply the outside of the parent function by a number larger than 1. So what it does is cause a vertical stretch by a factor of 2, right? So it's like all the y values get multiplied by 2. So if you just take the original graph, each y gets multiplied by 2, that's your new graph, right? Or you can put it in a graphing utility. It's totally okay. We're just looking at the graph and we want to see if it passes or fails the horizontal line test. Okay, so notice, and let's kind of stretch our horizontal line this time. Okay, so notice no matter where we draw a horizontal line, it only touches the graph once. We don't have a case of drawing a horizontal line and it touches it more than once. So this is an example of something that passes the horizontal line test. You good, it's okay. It's all good. No need to apologize. Everybody's doing the best they can. This is an example of something that passes the horizontal line test, and so we would say that this is indeed one-to-one. Okay? So also, if I'm talking too fast or anything, because this is asynchronous and this is a pre-recorded lecture, you're always welcome to like pause, slow down. You can actually change the speed of the playback. You can like slow it down or you can speed it up. You can rewind the video. It takes a little bit getting used to, but I prefer this style better. I'm not waking up hours in advance to drive to a location and say the same thing over and over. I can just make the video, say it once, and then we can talk about it with the different groups, right? I'm not like constantly like saying the same thing over and over throughout the day, which is draining and like annoying, right? I'll get paid to come. Y'all don't pay me enough to come. But anyway, that's me complaining and being a little bitch about it. But no, I mean, I prefer this. Like, I can kind of be wherever I want to be in the world. Like, my intent, honestly, is to be like on the beach or near the beach and still do the same presentation. And then when I'm done with you all, close it and I go live my life. I have to live my life. Like, that's number one. All right, I have to. I have to. Like, hands down. So, and also, I prefer this because I do encourage you all to just automatically just go ahead and link up with the tutors, right? I'm even open to considering offering extra credit. Like if you show me that, if you prove to me that you've linked up with a tutor, I can offer some extra credit for that. I offer at most 10% extra credit throughout the semester, and I usually give it in increments of 5 points, and 100 points will be 10% of your overall grade. I'm open to that. I'm open to some other forms of extra credit in the form of I do need an intro for my YouTube for my presentations on YouTube, and I need an outro. So I offered this to my other class, so I'll offer it to you. But I'd like to hold like a competition or contest where, okay, you all make an intro, and I'll have my students vote on the best intro, and then make a YouTube something, YouTube intro, and I'll vote, and I'll like whoever gets whoever wins the competition, they get the most extra credit, and then I will be open and like no more than three per in a group, right? So you can have teams of three, and then I'm also open to considering extra credit for the second place and third place runner up, first runner up and second runner up, right? So an intro, that competition would be like around midterms, and the outro, that competition would be closer towards the final. Also, I'm open to considering extra credit in the form of if you take like a concept that we've been talking about for that week and you present it during class, like present it, like do a YouTube short, uh, anywhere from 15 seconds to no more than 60 seconds. You make a YouTube short and you present it during class. If we have more than one, we're going to just make that a competition as well. No more than groups of three. I'm open to considering offering extra credit for that kind of thing as well. For the YouTube short, I'd like you to like take something we talked about for that week and either apply it to something in your everyday life or apply it to some topic that's relevant. Like we got the pandemic going on, we have a lot of strife around the world. So can you take something that we're talking about and apply it to something that's relevant for you or relevant to somebody else, right? You make a YouTube short for that, present it in class, and walk us through the concept of the idea. I'd be open to considering extra credit for that, right? So right off the rip, we got extra credit opportunities. Let's see. Yeah, so I just wanted to kind of throw that in there because I want you to be aware of it. Okay, so let's look at some of this definition. We have definition of f inverse for a one-to-one function f. So let f represent a one-to-one function. The inverse of f is also a function called the inverse function of f, and is denoted by f to the minus 1, right? So f inverse, this is read f inverse. So given an ordered pair, if x comma y is an ordered pair of the function, then y comma x is an ordered pair of f inverse. And we write x equals f inverse of y. We have y equals f of x if and only if f inverse of y equals x, right? So let's just we're going to kind of let that be and kind of move forward and see some of this stuff in action. So we're in this example, it says to assume that f is a one-to-one function. So we're given that it's one-to-one, right? It has an inverse. So if f of 3 equals 5, we're asked to find f inverse of 5, right? F inverse of 5. Now this is a little bit of a typo. This should be this. I'm just going to kind of write it over to the side. This should be f inverse of 5, right? So if f of 3 is 5, and we're given that this function is 1-to-1, we're asked to find f inverse of 5, right? So then for part A, because this function is 1-to-1, then that means that f inverse of 5 is just going to be 3. Again, because this function is 1-to-1 for part B, f inverse, or we're given f inverse, so f of 7 in this case is going to be -1, right? They kind of go back and forth, right? And I think we have a typed version of what we just did. So we got 3 and -1. So let x be 3 and y be 5. Now 5 equals f of 3 if and only if f inverse of 5 equals 3. So then I think 3 is the result there, right? And a similar argument for part B. It's a little bit wordy. It's not as complicated as it looks. It's just opposites, right? Given if a function is 1-to-1, that means it has an inverse. So given your order pair x comma y, what you consider an inverse function, they essentially just switch places, right? Let's see it. Let's keep going. Okay. So we have some properties of inverse functions. So let f denote a 1-to-1 function, then f of f inverse. So from College Algebra 1, this is composition of functions. Composition of functions is just a function, one function inside another, right? So we took f of x and we replaced all the x's with f inverse. So when we say f compose f inverse, a function composes inverse, they cancel each other out, and we just get x. For every x in the domain of f inverse. Again, this is supposed to be f inverse. And then the converse is true when they're 1-to-1. F inverse of f is also going to be x. Further, if g is any function such that for the values of x in these equations, f of g of x equals x and g of f of x equals x. So this is how we verify that one function is the inverse of another. If we wanted to verify that g is an inverse of f, then we need to show that f of g of x equals x and g of f of x equals x. Then we can say that g is going to be the inverse of f. Okay? Again, a little bit wordy. I feel like it gets better when you just work a few examples. And if my explanation is like not sinking in, this is where the tutors and your classmates come in. I definitely encourage you to automatically link up with the tutors. And then it's also a good idea. You want to have the contact of at least 3 of your classmates in all of your classes, right? So between the tutors, your classmates, and me and the internet, one of those, and what you do on your own, between those 5 sources, it should sink in. But it takes an effort of getting intimate with the information and sitting with it and keep processing it until it sinks in. If you can't get it on your own, then my recommendation is link up with your classmates. If it's not sinking in with working with your classmate, then I will go to the tutor. You definitely want to go ahead and seek out the tutors automatically. Just do that automatically. Have their contact and their schedule and all of that. But if you can't get it on your own, you can't get it with your classmates, it's not sinking in with the tutor, at that point, then that's the best time to come to me. If you come to me first, a lot of times the way I share or present it, it overwhelms the students and it kind of scares them and they shut down. But I feel like when the students do what they can on their own, and then they do what they can with their classmates, and then they do what they can with the tutors, by the time they come to me at that point, when I do the exact same presentation, then I can see the light bulb is very clear, and your chances of success are much higher. So hopefully you're able to like take advantage of that idea or that suggestion. Okay. So in this example, we're asked to verify the following pairs of functions are inverses of each other. So in other words, what they're asking us to do is show that f of g of x is x and g of f of x. Thank you. I thought I had my do not disturb on, but I did not apparently, so I'm going to put it on now. Okay, so again, if we want to verify that these are inverses of each other, we need to show that f of g of x equals x and g of f of x equals x. Okay, let me write that out. So I'm going to say we need to show f of g of x equals x and g of f of x equals x. Okay, so we just need to show these two things. Okay, so let's start with f of, now I'm going to do g of x in green. F of g of x, right? We're going to put g of x inside of f of x. So this is going to be f of, now what is our g of x? G of x is this x minus 3 over 2. So all we're going to do is rewrite f of x like normal, but we're going to replace all the x's with that green thing, right? So here's f of x, 2 times x plus 3. But now we're going to replace x with the green thing, which is going to be this x minus 3 over 2, right? So now we have one expression in one term. We can simplify at least. Okay. So let's see. I think this 2 is canceled by that one, and then -3 plus 3 cancel, and this leaves us with our desired x. So that one checks out. So then, now what color is fuchsia? Fuchsia is what, like a pink or something? Sure, why not? We got AKA colors going on here. Okay, so now let's consider the converse, right? We did f of g. Now let's do g of f. I said fuchsia because it's like, you know, hopefully this is okay. F of x, right? Just something that's vibrant. Okay, so this is going to be g of, now f of x is what, 2x plus 3. So now what we're doing, we're just rewriting g of x like normal, but we're replacing all the x's with that fuchsia thing, or hot pink. Right? So g of x is going to be x minus 3 over 2. Notice I start by replacing my x with a blank parenthesis, and then what goes into the blank parenthesis? Again, I chose quote-unquote fuchsia. Right? So then from here, we can lose the parentheses. The plus 3 is canceled by the -3. And then ultimately, the 2 is going to be divided by the 2, and we finish with our desired result, right? So now we show that f of g of x is x. We show that g of f of x is x. So then that's how we verify that two functions are inverses of each other, okay? And I think we have a type version of what we just did. F compose g, you see the x there. G compose f, you see the x there. Since f of g of x equals g of f of x, which they both equal x, we conclude that f and g are inverses of each other. Okay? All right. So now we want to consider this notion of the symmetry property of the graphs of f and g. F and f inverse. The graph of f and the graph of f inverse are symmetric with respect to the line y equals x, right? So what this means is when we look at the graph of f and we compare it to the graph of f inverse, they're going to be the same graph, but what we're going to do is take the graph of f and we're going to rotate it. It's a little bit of a challenge. You got to use your imagination, but we're basically rotating about the line y equals x, and that'll produce the graph of f inverse, right? So for instance, we have this example. The graph of the function f is shown, where x has sketched the graph of f inverse. So with something like this, all you really have to do is switch the x and y coordinates, right? So if we want to just see the graph of f inverse and we want to rotate about the line y equals x, instead of plotting -1, 2, f inverse is going to be the point 2, 2, comma, -1, right? This one's going to be 3, comma, 4. This one's going to be -5, comma, -3. So if we plot those points, and then connect them in a similar fashion, that will be the graph. And matter of fact, we can go ahead and do it. 2, -1 is here. Boom. 3, 4 is here. There. And I'm going to move this next to this. Right there. This one's kind of already, undo. This one's kind of already next to this guy here. And then the final one, -5, -3 is about here. Okay. And I'm just going to kind of move this there. And then we can connect these. I can use blue, it's fine. With a straight edge. So like here to here, and then here to here. Right? So the blue is now the graph of f inverse. And basically essentially what we did, we rotated about this diagonal y equals x. Let me kind of try to get it there, about there. And that's essentially what it should do. We're going to go style. We're going to thicken this up and make it a dash, about like that, a little bit thinner. And that's essentially what we did. We essentially rotated about this green diagonal. Okay, hopefully that made sense. All right, and we have a computer generated image of what we just did. Oop. Oh yeah, that's fine. Okay, so here's what we did by hand, and then here's a computer generated form. Okay. So we've seen graphically what do we mean, like how to produce the graph of an inverse function given the original function. We've talked about this in the sense of correspondence diagrams to a degree. So now we want to see an official procedure for finding the inverse function. So given some f of x, how do we find the inverse? So we have this four-step procedure where first we're asked to replace f of x by y in the equation for f of x. Then what we do is switch the x and the y's. We solve for y from step 2, and then now this is going to be the equation or the function for our f inverse, right? Let's see this in action. So we're asked to find the inverse of this one-to-one function. So we're given that this function is one-to-one, and notice that x cannot be equal to 2. We're going to let that be for now. Okay? So find the inverse function, right? So the first step we're asked to do is replace f of x with y. So we're going to rewrite this as y equals, we got x plus 1 over x minus 2. Okay? So then the next step that we do is we switch the x and the y. So all our x's and y's switch place. They switch places. Okay? And so it's going to appear in the following way. Over here we're going to have x, and here we'll have our y, right? So we're going to have y plus 1, we're going to have y minus 2, and this is equal to x. So we essentially just switch the place of the x and the y. Now we want to solve for y. So now to do this, what I'm going to do, I'm going to start by multiplying both sides by y minus 2, and this by y minus 2, right? If I do this, these guys cancel. I'll continue like over here. On the left, we're going to have, and I'm going to go ahead and distribute. We have this xy minus 2x equals y plus 1. Now we're trying to solve for y. So what I'm going to do, I want to isolate my y's on one side of the equal sign and everything else on the other, since I'm trying to solve for y. So I'll do this by, I'll subtract y from both sides, and I'll add this 2x on both sides. Okay? So now when we do this, these cancel, and what we get on the left, we have xy minus y. On the right, we have 2x plus 1. On the left, we can factor out y. We're left with x minus 1 equals 2x plus 1. Okay, and then divide both sides by x minus 1. Ultimately, we get y equals, because I'm running out of space, I'm going to go ahead and write that as f inverse will be equal to 2x plus 1 divided by x minus 1. And it looks like x cannot be 1. Okay, but I'm going to leave this like this for right now. Okay, here, and then here, I'm going to go start like this, right? Let's see what the type notes say about this. Okay. So first they replaced f of x with y, then they switched the x and the y, and then they solved for y. They multiplied both sides by the y minus 2, distributed, got the y's on one side, x's on the other, and then they get here, right? Same place that we got to. And again, we can't divide by 0, so x is not equal to 1, so that's fine. I'm going to go ahead and add that to our text. And let's do this. Let's say comma x is not equal to 1. And I'm just going to expand this out a little bit. And just so it fits properly, I'm just going to do this really quickly. I think I got everything. I'm just getting it to fit in this space. Okay, that looks good. Okay. So we're good there. I think we got the same thing. Okay. So now in this one, we're asked to find the domain and range of this function. So off the rip, you can see that x cannot be 2, right? Because we can't divide by 0. Let's go ahead and find the inverse function. Didn't we just do that one? Isn't it the one we just did? Okay, so if that's the one we just did, right? I think initially we said, so for f, f we said that what? X cannot be equal to 2. For f inverse, we said x cannot be equal to, I think it was a 1, right? So then that tells us everything that we need to know for domain and range. So what this means is the domain comes from f, right? So the domain of f is basically everything except 2. So the domain is going to be everything except 2. So we're going to say negative infinity to 2, and then from 2 to infinity. Infinity always gets parentheses. Because we don't want to be equal to 2, the 2 gets a parentheses as well. Parentheses means we get, in this context, we get close to that number, but we never reach it. And then we combine these two sets with a union, right? So this is how we express everything except 2. The range is basically the domain of the inverse. So the range of f is everything except 1. So we're going to say negative infinity up to 1, and then 1 to infinity. In this context, infinity always gets parentheses. Because we don't want to be equal to 1, we use a parentheses, and we combine those two sets with a union, right? So the range of f comes from the domain of f inverse, right? So this is the domain and the range of f. The domain of f is the set of all real numbers such that x is not 2, so you see it here, everything except 2. The range of f is the domain of f inverse. So for this, this can be equal to any real number except 1. So we had to throw out the 1. So that means the range of the original is going to be everything except 1. Okay. Find the inverse of this. So we note the domain that x has to be greater than or equal to 0. Now, notice that this is a parabola, right? We started with a U-shaped curve, and all we did was move it down by 1. But this domain says that x is greater than or equal to 0. X is positive. This is going to correspond to the positive part of y, right? Let me think if I can think about a better way to explain that. Yeah, we got to decide, like, does this correspond? Because if we're going to have, like, what, a positive y or a negative y? Let's go ahead and do our procedure that we did before for finding inverse. So if we're starting with g of x equal to x squared minus 1, okay? So first we replace the g of x with, like, I'm just going to replace it with y. Then I'm going to switch my x and y. They're going to switch places. So I'm going to get x equals y squared minus 1. Now when we solve for y, like for instance, if we add 1 on both sides, I'll just go ahead and put plus 1 and plus 1. Okay, I just added 1 on both sides. On the left, we get x plus 1. On the right, and these guys cancel. We get y squared. Now we go to take the square root on both sides. But remember, whenever we take square root, we need to include plus or minus, right? And these guys cancel. So we have the positive square root versus the negative square root. I'm trying to think if I can give you a clear reason. I think you might have to just try a few numbers to confirm. Like, for instance, if x is positive, like if x were 1, right? If x were 1, 1 squared is what? 1 minus 1 is 0. So then y should be 0. Let me see. Am I missing something? What happened? I added 1 to both sides. I took the square root. So this is f inverse. So for instance, when x is 1, we get 0. So then when x is 0, y will be 1. I'm gonna probably rely on the notes to think of a clear way to explain that. But you could choose several values of x, find the corresponding y, right? For instance, um, let's do when x is 2, right? If x were 2 from here, 2 squared is what? 4 minus 1 is a 5, which is positive, right? So because of that is why we're going to take the plus over the minus. That's why I was hesitating, trying to convince myself and you all why are we taking the plus over taking the minus, right? Because whenever we put x in here, the output is giving us positive y values, not negative y values, right? Okay, that's where my hesitation was coming, but I got to the bottom of it, right? So now we get y equals this, and we get plus or minus, but for this context, we're only going to take the plus. So then, long story short, we're going to get f inverse of x equals the positive root of x plus 1. Now, with these examples, I probably should look at them in advance, but I typically don't. And I do that kind of intentionally because I kind of want you guys to get a feel, like if you at least are aware or know the techniques, then how to think through these or how to reason through them, right? And it's important to work with others because my technique a lot of times I really feel like I'm just here to show you that it's possible, but you got to find something that works for you as often as consistently as possible, right? I'm showing you that hey, it is possible to work these things, but it's up to you to kind of find something that works for you. Consistently. And you do that by sitting with it yourself, researching, working with your classmates, and linking up with the tutors and asking me. But if you ask me, I'm more than likely going to say this is the exact same thing that you see here, right? So you want to get as many perspectives as you can. That's the recommendation. Okay. So we get this for the inverse. And notice here, again, we can't take the square root of negative numbers. So the x plus 1 has to be greater than or equal to 0. Long story short, for that domain of the inverse, x plus 1 has to be greater than or equal to 0. If we simplify or solve for x, then we say that x is greater than or equal to negative 1, right? So the domain of the inverse is x is greater than or equal to negative 1. That tells us the range of the original. So I think this is what we needed. This is what the question was asking for. The inverse with this domain. We're going to go with this. Okay. I've been talking like I went on and did my calculus course before you all. I'm just making it. I'm trying to make as many things in advance as I can. I have loaded all. Okay, let me make this statement because I don't know. I don't think I've shared this with you all. But I have loaded all of your homework quizzes and all of your exams on Pearson. You can access all that information except for the exams, right? So your homework for the semester and your quizzes for the semester, you can access them now. You can earn full credit on any of those assignments from now up until whatever due date is associated with those assignments. You can actually work on any assignment past the due date with only a 10% late penalty. However, there is a hard deadline of, I think it's like May 1st, which is a Sunday night going into Monday night at midnight. That's the hard deadline for everything. That's like going into the week of finals. The idea is that when you take your final exam for this course, that's it. I don't like no lingering assignments, nothing due. I don't want you trying to finish things past the final, all right? So each assignment has its own deadline. You can work, and as long as you push and submit it before the deadline, you can earn up to 100%. Past the deadline, the highest you can earn on an assignment is 90%, all right? Exams included, and we get unlimited attempts at all of our assignments. Okay, we're actually almost done with this section, so we're going to kind of press forward. We got square root of x plus 1, and you see it there. I don't think they kind of mentioned the domain, but that's okay. And we have a graphical representation, right? So for G was the right-hand side where x was positive, the right-hand side of a parabola. So then when we rotate about the line y equals x, this is just the top half of a sideways parabola, right? And you can see where it's been rotated about the line y equals x, which is that green diagonal, okay? So then we have this example on water pressure on underwater devices. The formula for finding the water pressure P in pounds per square inch at a depth D in feet below the surface is given by this guy right here, right? Suppose the pressure gauge on the diving bell breaks and shows a reading of this. Determine how far below the surface the ball was when the gauge fell. So let's see, PSI in feet, pounds per square inch, the formula. Okay, so it says it breaks showing a reading of 1800. So the P is 1800. They're basically asking us to solve for D, right? So two ways we can go about this. We can plug in 1800 for P and then work backward algebraically, or we can use inverses, right? Notice that this function is linear. The highest degree is 1. It should be a diagonal line with a y-intercept of 5 and a slope of a positive 5 over 11, right? So it should be a diagonal line, which means it passes the horizontal line test, which means it has an inverse. So let's apply the notion of inverses and let's just go ahead and find the inverse. I'm going to use the space that I have. So we have P versus D. So what I'm going to do first is switch the P and the D. I guess we should give ourselves some space. So let me start by getting a copy of the original. We have this P equals 5D over 11 plus 15. So I'm going to take this, I want to cut, and I'm going to add it to a page, a blank page, and we can kind of expand it out. And I am a fan of writing on lined paper. I usually do a spacing of 2, hit done, boom, right? So here's a copy of that question. Now, this is the original. Let's go ahead and find the inverse. So to find the inverse, we're gonna switch places of the P and the D, right? If we do this, we'll get D equals 5P over 11 plus 15. So now we can just, I think we were also given that P was 1800, right? So we were given that P was 1800 PSI, pounds per square inch. So we can take that 18 and just plug it in and it'll give us the depth, right? So this is going to be 5 times 1800. Again, you can use calculators over 11 plus, what is this? It's just tripping. Let me go like this real quick. Can I get you to, there you go. Sorry about that. Plus 15, all right? So then we just crunch the number. 50 plus 40 is 90 with 2 zeros on the back, divided by 11 plus 15. I'm going to do this by hand. How many 11s are in 90? It's 88, so that's 8. You have a remainder of 2, so 20. So then that's a 1 with a remainder of 9. 88 is 8 again. Remainder of 2, so 20. I think it kind of repeats. You got a 1 with the 9. 90 is 88, which is 8. Remainder of 2, 20. So I think this repeats. It just keeps repeating the 18, right? We could find that fraction, but I'm going to leave it like this for now. Plus 15. Yeah, we could find that, and I'll do a demo on that momentarily. If we add 15 to this, let me see. 8 and 5 is what? A 3. You carry the 1, so that's a 3. 8. 18 bar, right? Okay, so what depth? I think this is in feet. And let's do a quick little exercise. Let's see how to convert that repeating decimal. Again, I don't know if this is correct or not. This is just when I was working it, this is how it came out. Okay. So let's see a quick demo on how to convert repeating decimals to a fraction. Okay, so this is just a side note. This is just something extra. So if we consider 0.18 bar, right, and we want to convert this to a decimal. So what I'm going to do, say this is the x that we're considering. Now what I'm going to do is look at another number that has the same repeating decimal. So what I'm going to do is multiply this by 100 because we want to have the same repeating decimal. So I'm going to say this times 100 and this times 100, right? If we do this, then we'll get 18.18 bar equals 100x, right? So now if we combine these two expressions, like I'm going to say the 100, the second line minus the first line, if I subtract these two, 100 minus 1 gives us a 99x here. 18.18 bar minus 0.18 bar is just 18. So now if we solve for x, divide both sides by 99, x equals 18 over 99. I think both of these are at least divisible by 3, right? We can factor out 3 at least, maybe even 6, but let me do the 3 first. 18 divided by 3 is what? 6. 99 divided by 3 is 33, but we can do another 3 from there. So 6 divided by 3 is 2. 33 divided by 3 is 11. All right? So that 0.18 bar should be the same as 2 over 11. So I'm just going to write 833 and 2/11 feet. So that was just a side thing. It doesn't hurt to know how to convert repeating decimals to fractions. Okay. So when we did it by hand, we got this. Let me go to templates and get rid of this line. Hit done. Okay. When we did it by hand, we got what you see here. Now let's compare. Hopefully, now again, I make mistakes. It's okay. You know, we just do our best to not make the same mistakes over and over. Okay, so we got 833 and 2/11 feet, or 0.18 bar repeating. Solve the given equation for D. All right. Oh, we're way off. They solved for D. Let me think about it. Let's see. So let's see, what do we do? P. They multiply both sides by 11. Wait a minute. We found the inverse. Okay, yeah. 11. Maybe we made a mistake. 11p. Wait a minute. Because if I'm looking at what they did, and I didn't even check to see if like our answer made sense or not. But if they multiply both sides by 11, like to get the 11 from here to here, this times 11, I agree. This times 11, I agree. This times 11, I disagree. Right? So this is not correct. Did they switch them? They didn't switch them. So they solved for D. Let me think about it. Yeah, this looks like a typo. Let P be 18 when the gauge fell. 39.27. Let me give me a moment. The pressure. Something is off. 5D. Let me solve for D. Let me try their technique of solving for D. I'm going to do this in like this dark green. So now if we have P equals 5D over 11 plus 15, and if we solve for D from there, right? If we solve for D, yeah, even if you, so like for instance, if you subtract 15 from both sides, you get P minus 15 equals 5D. Subtract, sorry, 5D over 11. If you multiply both sides by 11, you'll get 5d equals 11p minus 150 plus 15, 165. Right? Now, if you divide, maybe it works out. If you divide both sides by 5, d equals 11 over 5p minus, what is that, a 3, 15, 33. Okay, I think they got the, no, but we got the 33. They got it too. 11p over 5 minus 33. Switch, right, where'd it go? Oh, wait a minute. You switch, oh, maybe I forgot to solve for p. They gave us p. Oh, I think I did the inverse improperly. Okay. Yeah, I never solved, right? What did they give us? I think I just overcomplicated it. P, right? The D would be equal to, yeah, I don't know why I did that. I mean, okay. So yeah, what I did was not correct. If we plug in P equals 18, we could have just did that off the rip and solved for D. I don't know why I was doing it the way I did it. I was trying to use the inverse. So if we had put that into the inverse function, then it would have gave us the right. I never found the inverse. I just switched them and then started crunching the number. I never found the inverse. So that's where I kind of made the mistake. So I'm trying to think if I want to. I'm gonna leave this just to leave it. Right. This is the problem is I didn't actually find the inverse. I just switched their position. So I needed to still go ahead and find the inverse. Um, like okay, let me fix it. So after I switched it right here is where I went off. So I will do that. Let's use orange, right? So now if we find the inverse there, so if we solve, we switch the P and the D, then what do we need to do? Why do I feel like that's making it worse? Let me think about it. If we solve for P, because basically what we'd have to do is subtract the 15, multiply by 11, and divide by 5. Yeah, but I feel like that's making it worse. Okay. I just messed up the inverse there. So I guess the more simple thing would be something of this nature. Another way we could have done it. We could have just done 1800. 1800 equals 5d over 11 plus 15, right? We just plugged in for p and then solve for d there, right? You can subtract your 15. So if we subtract 15 from both sides, we get 5d equals 18, 1790, 1785. Subtract 15 over 11. You can. That seems like that gets kind of big fast. What I'm gonna do is say d equals. It's gonna be 11 over 5 times the 1785. Right. Okay. So then you just crunch the number. I'm kind of out of space. I'm gonna kind of work here. So if you divide by 5, for instance, this is going to be 11 times. If it's 15, there's 3. 28 is 5. 35 is 7. But I feel like yeah, I think that's okay. So then that's going to be 3570 plus another 357 gives us 2 carry the 1, 9, 39, 27 feet. So I think the problem that I did with the other one, I just never found the inverse. Like I just switched them and then started crunching, and that's where the trouble came. 3927, 3927. Yeah, that was my fault. I totally messed up on the other one. But again, I'm tired. I'm about to fall asleep. But we found a mistake. We fixed it. It happens. Okay. Let me cross off. So it was all of this stuff here from basically from here. All of this was wrong. And I'm leaving it because I still want you to see like that technique of finding converting a repeating decimal to a fraction. That stuff is good. The orange is like the correction. We just plugged in the 1800. You know, I think we've seen a couple of ways of doing it. I'm gonna leave the error there, just because that's the nature of it. You don't always get it right off the rip, but as long as you can find the mistake and correct it, that's what's important. Okay, and so that's a lesson. Like we have to kind of keep that stuff, but it's okay. So it was 39.27 feet below the surface when the gauge fell. Okay, well, them the breaks. That's how it goes. Okay, so that wrapped up section 1.7, which is an intro to inverse functions. Um, let's see. So again, I have loaded all of our homework and quizzes, and I've scheduled the exams for the semester, but you won't have access to the exams until we get closer. So I think we're scheduled to have 3 exams and a final. Our exams for this course occur during week 4, week 8, and it's like 13. It's usually 12, but because of spring break, it kind of throws things off. But I think it's like week 13 or 14, one of those two. It's 3 exams and then the final exam. And right now, everything is scheduled for Pearson, which you access from Blackboard, right? So you will go to Blackboard. You do have to purchase full access. I'm under the impression it should run you about $120. But the thing is, as long as you're using the same book, going forward in other classes, you don't have to purchase it again if the professor's using Pearson, okay? If we have questions, the best time to contact me is just during class. So my intent is to use class time as a study session. I do these recordings in advance to free up time during class. Time during class, we're kind of like jammed. We're cognizant of time. You know, we're very limited. So I want to maximize that time. So I do these in advance so we can use class time as a study session. Uh, my recommendation is to watch these videos in advance, take notes as if you're in class, and then come to class with questions. My experience have been where students just generally don't come to class with questions. I'm pretty sure that they were not watching the videos. But they found a way to get through the material, right? But I'm just covering my tracks and making this stuff available. But my recommendation again is to watch this stuff in advance, take notes as if you're in class, and come to class with questions. If you don't have questions, generally what I do is I work through as many homework questions as I can. But everybody still has to do their own work and submit their own results because everyone still has their own set of questions. It'll be the same questions with like different numbers, and you still have to do your own work. Okay. So with that note, hopefully you can create a plan of attack and execute. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, take care. Peace.